Welcome everybody to today's IGS seminar. And we have three speakers today, again, three early career scientists, which are Erik Loebel, then afterwards it's Elise Kazmierczak and Danielle Halle. And yeah, we start with Erik, and he is a PhD student at TU Dresden. And his research aims at developing and applying AI methods for monitoring glacier changes in Greenland. And furthermore, he is co-chair of the German National Committee of the Association of Polar Early Career Scientists, or called short APEX Germany. And yeah, with this, you can start.
Okay, so, oops, you see the slides now?
Yes, we do.
Okay, so thank you a lot for the introduction. So this talk will be about how we apply AI, or specifically deep learning, in order to automatically extract glacier calving fronts from satellite imagery. So as an introduction, let me briefly introduce you to the motivation of our work. So this schematic now shows a typical marine terminating glacier. And we have a lot of environmental factors which affect this glacier. So this could be forcings from the ocean, the atmosphere, bedrock topography, or hydrological processes. And understanding or even modeling all these interactions is, of course, very far from trivial. And calving, which is right at the center here, this schematic plays an essential role, because not only does it deliver us direct observations of retreat or advance of this glacier, but as it affects the stresses of this glacier, it is also a very important or an even essential indicator for dynamic changes. And furthermore, of course, if we want to get the sea level contribution of an ice sheet or a glacier, we basically rely on computer models that try to simulate this behavior. And without an reliable parameterization of this calving, these models are very poorly constrained. And but so what do we need for an accurate parameterization of calving? Actually, it's not too complicated, because we only need the glacier calving front position, so the position of the calving front, but we need it at a good temporal resolution. So we need a lot of observations. Thankfully, right now we are living in a very good time to achieve this task, because we have a huge amount of satellite data available to us. Here only showing some of the commercially free and popular programs like Landsat or the Sentinel program. And using all the satellite data, it should be possible to process large, dense, and very comprehensive data sets of calving front locations. And although there have been a lot of research and advances of this in the past, only now with advances in machine learning and big data, it is truly possible to create those robust and accurate and scalable processing strategies. And this is basically where our research starts. So we create tools, methods, and data products for the glaciology community to work with. So let me show you how we try to achieve this. So this is a very broad overview of our processing workflow. So we have our input information, so our satellite data here on the right, and our calving front position we want from this satellite image. No, here on the right, so that was on the left. Okay. So in this talk, I'm gonna mainly focus on the results and the glaciological implications of these results, but I still want to provide some important points on this method here. Because on the input data, we focus on Landsat 8 imagery, and thereby we have a good opportunity to really make use of all the multispectral information. So we not only use the visible satellite bands, but also in the satellite information in near, shortwave, and thermal infrared. And now, using this stack of satellite information, we apply an artificial neural network to perform this land cover classification. And with land cover classification, I mean that we basically put every image pixel, in our case, either in a water or a glacier and land class. And yeah, I think most of you will know where this is going. Of course, our glacier calving front in the end is a boundary between these two classes. So we have to vectorize our model prediction and then mask out the final calving front position. So the main part of this processing workflow is basically this artificial neural network here that does land cover classification. And of course, with all machine learning or deep learning algorithms, we need reference data in order to train this algorithm. So, and this is a very important step because, of course, we needed to train it, but we also need the data to validate the algorithm. So in the end, if we have a model, we can't just use it and say it works fine. We have to really, validate the results there. And to create this reference data set, we use manual delineation. So basically, we use satellite images which are digitalized manually to basically fit this model. So it does it automatically afterwards. So on there we created a manual, a data set with manual delineated satellite images. So we have about 700 images. You see a map here on the right. So we focus on the Greenland ice sheet, and you see all the glaciers, and the time frame we have is from 2013 to 2019. And of course, this training data set is highly important because we have to consider a lot of different different aspects like cloud cover, different ice and ocean conditions, illumination, because in the end, our final algorithm is only going to be as good as the data we train it with. Furthermore, we need to validate our algorithm. As mentioned, there we use another 200 images on a different time frame. So here we have 2020 and 2021, and we also have some additional glaciers to really ensure that we have this spatial generalizability to afterwards that we're able to apply this algorithm on any glacier. And then we use some additional glaciers from some established data sets, like from ESA CCI and from calving. So these are also manual delineated glaciers we use for testing our model. So now let's have a look at some of those testing images. So these are images that are basically unseen by our AI model. And we already see, let's start the automated calving front predictions in these images are in yellow color, and in the dashed black we have the manual delineation, so a human delineating this image. And we also have denoted on those images the mean distance between those two trajectories in meters and in pixels. And we see here already on this image that the delineation, the automated delineation works quite perfect because we have like here an open ocean part, we have like transition to ice melange, icebergs, and different ice melange conditions, and the algorithm works very well in detecting all these different patterns and delineating the calving front accurately. Similar on this image, it's actually a glacier in Svalbard we just introduced here. And here we have like this fast ice with snow cover, which is also very different in texture, still very accurate delineations. Maybe this image as well is quite interesting because here we have this challenging illumination in those narrow fjords. And we still get good delineation, and this is mostly due to the multispectral data we introduce, especially in this case, the thermal data, which of course still has some additional information which helps in these problematic conditions. Two more examples here on the left side from Humboldt Glacier. We see that near the calving front we have like quite large icebergs which are basically hang around at the calving front. And we already see a problem here, like smaller or differences between the AI and the manual delineation. And of course, it's quite complicated to get the delineations here. Even if you put like 2 humans on this image, you might get different results because it's quite subjective and hard to tell which iceberg is already calved and if it's still attached. So this is something to consider when looking at those accuracy estimates. Similar here on the right side, this is the Cairns Glacier, which has like the seasonal ice tongue almost every year. And there we also have quite some subjectivity depending on the person who's delineating this. And of course, our model is always trained to delineate it the way that we force it with our training data. So here now on the left we have like this broad overview. So we trained 50 models in total and applied them each. So each horizontal line is one trained model and applied them on our 3 testing data sets. And here on the y-axis we have the basically our error estimate, which is the manual delineation distance. And we look both at mean and median. Of course, the mean is more sensitive towards outliers, so very challenging scenes with large errors. But the important thing to take away from this figure is maybe that if we look at those numbers here, that we are well below a 100-meter distance to manual delineation, which is a very good result, considering that if we compare like author to author errors from different calving front delineations, we are also in the range of 100 meters. So we can conclude that basically our algorithm, the calving fronts provided by our algorithm have a similar quality to those provided from a manual delineation. And more often than not, they are indistinguishable from them. So now that we know that this algorithm is working well, we apply it to Greenland. So this figure now shows basically the product we have for Greenland glaciers. So you see for almost all of our glaciers, we have like sub-weekly sampling outside polar night. And I'm showing here one example. This is like for Sverdrup Glacier in West Greenland. And on the images on top, you see basically the algorithm working on the Landsat imagery. So it's delineating the calving fronts, and we apply it with this like box method. So we basically quantify the calving front change by looking at the area, and this you see at the time series at the bottom. And here it's quite interesting that we have this like really pronounced seasonal pattern from this glacier, but also like a long-term retreat we see basically on top of this. So to also show some more examples, of course, we could apply this to many glaciers as we want, but here maybe some interesting ones. So we see the seasonality for almost all Greenland glaciers, maybe except like Wider and 79 North Glacier, which have more like this steady retreat with the break-off of larger icebergs. And of course, notably maybe Humboldt Glacier and Sararia Iström, we see like a retreat of more than 100 square kilometers, which is also quite a lot. Interesting are also those glaciers where we see like a change in calving rate, like here in Harald Moltke Bre, where we have like this faster retreat in the last years, which is due to the stopping of the surging phase, which was like about 6 years. And other glaciers like Ingia, Isbre, where we're gonna look at in the next slide, we have this interaction with the topography, which is also quite interesting. So here at the bottom, you see that we have a profile basically along the central flow line, which is what you see now here on top. And along this profile, we now have our calving front moving. And again, with the time series here at the bottom. And the interesting interaction here is, of course, that we have this topographic minimum. So you can maybe in a few moments spot that the glacier is accelerating down, like on this retrograde slope. And I think after 2018, it reaches this topographic minimum. And there we see basically a lowered seasonal amplitude, and it's basically remaining in this position for the next years. So this is quite interesting. I'm gonna jump to the next slide, because here we already have like this this aspect in a static figure, so we can really see that from 2019 to 2021, this glacier stays in this position. There are more examples of Dogard-Jensen. So we have this topography change point here, which affects the calving into a more to calving of larger icebergs, since we have like this floating ice tongue. And also Kangerlussuaq Glacier, which has like this, which is just before this tipping point to a steep retrograde topography, which continues actually for another 6 kilometers. So this is something we have to monitor closely, because we might expect some acceleration of the retreat in the future. So this also already brings me to the key takeaways of this talk. So of course, parameterizing of calving is essential for a number of reasons: glacier dynamics, constraining ice sheet models, and basically we have, with deep learning, we provide an effective tool for mapping these conditions, for mapping these calving fronts, and we are going to present the method and also the data product you just saw for many more glaciers in an upcoming publication, probably, which is going to be submitted this week. So you can look forward to this if you're interested, and then I thank you for the attention.
Thank you very much for a very clear talk. I really like it. And as always, we do questions in the end. So first we have all our 3 speakers. And our next speaker will be Elise Kazmierczak, and she is a PhD student in ice sheet modeling at the University Libre de Bruxelles under supervision of Frank Patin. And currently she is investigating hydrological and geological controls on marine ice sheet sensitivity in Antarctica. And then she's also part of the Protect group, and she is an active member of the chairing committee of APEX Belgium, and is deeply involved in science outreach. And with this, Elise, you can start.
Okay, do you hear me and do you see my slides?
Yes.
Okay, perfect. So let's go. Hi everyone. As folks already said, I'm Elise Kazmierczak, and I'm a PhD student from University Libre de Bruxelles. I am also a teaching assistant in glaciology and geomorphology. I am working for Frank Patin's lab in ice sheet modeling, and my study is more focused on basal conditions controlling the Antarctic ice sheet dynamics. I am very interested in my subject, which studies phenomena hidden under kilometers of ice, and I hope I will succeed to share with you this excitement about this topic. The results I will present today are published in the cryosphere, so for more details, don't hesitate to consult it. We know the Antarctic ice sheet is the biggest freshwater store on Earth, and we know Antarctica has been losing mass at an accelerating rate, especially in the western part. The future mass loss of this ice sheet represents the largest source of uncertainty, and some of these uncertainties are linked to subglacial properties which impact the basal sliding. The subglacial properties considered in this study are the kind of subglacial water drainage system and the rheology of the bed, which can be hard and non-deformable or soft and deformable. Subglacial water is due to basal melting or comes from supra or intraglacial water. This second source of subglacial water is not applicable for Antarctica. Direct observations of this subglacial water in Antarctica is quite difficult because of the ice thickness. However, drilling satellite and radar data has enabled us to locate some bodies of subglacial water. You can see on this map subglacial rivers and lakes found in Antarctica, such as the famous Lake Vostok, discovered during the 70s, as large as half of Switzerland and located under 4,000 meters of ice. These examples do not represent all the subglacial water drainage systems we see in other glacial environments, which are probably present under the Antarctic ice sheet, even if we can see them. The elements of subglacial water drainage system are classified in two categories. The fast and efficient water drainage system, which includes different kinds of channels, and the inefficient water drainage system represented by slow water flow, distributed as a thin film circulating between ice and bedrock in linked cavities or in the porosity of the till. All these processes lead to a lubrication at the bed and therefore play a role in the basal sliding of the ice. Indeed, recent studies have shown that in the case of ice caps, high subglacial water pressure is directly linked to areas of fast ice flow, and the subglacial outflow impacts the stability at the calving front or at the grounding line by subshelf mantling. In Antarctica, the subglacial water drainage systems are close to steady state and are seasonally stable. The subglacial hydrology will have an influence on the ice sheet dynamics by modifying the basal sliding. We know that ice caps are moving thanks to two phenomena. The first is internal deformation, meaning that the ice moves under its own mass. The second one, which interests us today, is the basal sliding. The basal sliding represents the ice movement above the bedrock. Basal speed and basal stress are linked by a nonlinear power relationship multiplied with a basal sliding coefficient, which is constant and includes basal properties. The basal stress is a shear stress parallel to the surface contact between ice and bedrock and slows down the ice at the base. It's a function of ice thickness and its surface slope. M is the sliding law exponent, taking integer values. The greater the value of M, the more plastic the basal flow of ice will be. This basal sliding law is better known as the power law. To link the subglacial water and the basal sliding, we will use the power law proposed by Budd in 1979, which underlines the importance of the subglacial water in the basal sliding law by adding the effective pressure to the power law. The effective pressure, called N, is the ice pressure minus the subglacial water pressure and will influence the basal coefficient in a specially varying way. For our research on the influence of subglacial hydrology on basal sliding, we use a numerical model to simulate the Antarctic ice sheet behavior on different spatial and temporal scales. For our investigation, we try to link different representations of subglacial hydrology with basal sliding laws. When I say sliding laws, it's the Budd sliding law, but with different exponents. Our research focused on Antarctica as a whole. As such, we only consider distributed simplified water drainage systems, which are more representative at this scale and easier to express mathematically. The subglacial water is therefore represented as a thin film of water located between ice and bedrock or in a porous till. These different representations can be considered as a decoupling level between ice and bed and act to enhance the basal sliding. To link these to basal sliding laws, we will use two consistent parameters: the subglacial water pressure between ice and bed or inside a till, and the subglacial water pressure will be included in the calculation of the effective pressure, and also we will use the subglacial water flux. These coupling options will be compared to a control simulation without any subglacial water consideration. So we have 5 different ways to couple subglacial hydrology with 4 different basal sliding laws, and it leads to an ensemble of 20 Antarctic model simulations. So the first representation of the subglacial water, so called the HAB representation, it will be easier for you to understand after that the results. So HAB, for height above buoyancy, is a water layer between non-deformable hard bed and ice, coupled in the model by its pressure. You can easily see on the figure that the subglacial water pressure is directly linked to the bedrock elevation below sea level. The second representation, the till representation, is a soft deformable till saturated by basal melting and also coupled by the pressure. In this case, the effective pressure is a function of the properties of the till, like its porosity, compressibility, and the thickness of the water in it. You can see on the bottom figures the link between basal melting and subglacial water pressure. The values equal to 0 in the basal melting figure correspond to places where the ice is assumed to be frozen with the bed. The last representation of the subglacial water is a thin film of water that is the product of basal melting, which evolves as a function of the hydraulic potential on a hard, non-deformable bed. You can see on the map of the subglacial water thickness that the film is of order of few millimeters. This representation can be coupled with the basal sliding laws by the pressure or the flux parameters, both function of its subglacial water thickness. These two options will be called SWD, so in dark blue for the coupling with the subglacial water pressure, and SWF in light blue for the coupling with the subglacial water flux. We initialize the basal coefficients using input data for each of our hydrology sliding coupling options. It consists of finding the values of these coefficients that results in a realistic ice sheet geometry when compared to observations. After initialization, we perform a historical run. This means that we give to the model data observed during 10 years in order to obtain an ice sheet geometry similar to 2015. Starting from the Antarctic ice sheet geometry of 2015, we perform different experiments. Experiments following the present-day conditions, experiments following realistic forcing scenarios, and experiments following extreme forcing scenarios. All these runs start in 2015 and end in 2100. The no additional forcing scenario, considered as a control experiment, is used as a benchmark to compare the other results. The realistic scenarios follow three different atmosphere-ocean general circulation models, so AOGCM, with specific surface mass balance and specific ocean thermal forcing under RCP 2.6 and 8.5. These scenarios are taken from ISMEP6 experiment described in Cerisi et al. 2020. The two extreme forcing scenarios taken from ABUMIP experiments in Son et al. 2020 are used to sample the intrinsic sensitivity for the full set of subglacial characteristics. One of them, the ABUK experiment, destroys the ice shelves at the start of the experiment and does not allow them to regrow during the run. The other, the ABUM experiments, apply a high constant melt rate of 400 meters per year underneath the ice shelves. These different kinds of experiments allow to better understand the real subglacial control on ice sheet flow. On this figure, you can see the sea level contribution from 2015 to 2100 in the ABUK forcing scenario, so the scenario for which all the ice shelves are completely removed. Colors represent the subglacial hydrology, so in black you have the no subglacial water consideration, in burgundy the height above buoyancy, in dark blue so the film of water linked by the subglacial water pressure, and in light blue the film of water linked by the subglacial water flux, and in orange the till model. And the different dotted types represent the different sliding laws. The sea level contribution from the Antarctic ice sheet will vary between around 2 and 6.5 meters. And it is clear on this graph that the choice of the sliding law is the dominant factor of the Antarctic ice sheet sensitivity. However, subglacial hydrologies will modulate the sea level contribution around 0.5 meter, and subglacial hydrologies reducing the effective pressure in the grounding zone, so the HAB and the SWD options, increase ice sheet's sensitivity to forcing. ABUM experiments show the same conclusions than ABUK, but with lower intensity due to the lower intensity of the forcing itself. For realistic forcing scenarios, the different sliding laws are represented in their own graphs for better reading. it shows in a global analysis a less clear influence from the type of the sliding law. We can still observe a modulation of the sea level contribution from the subglacial hydrologies of several centimeters. Again, HEB and SWD, which reduce the value of the effective pressure in the grounding zones, increase the Antarctic ice sheet sensitivity. All the realistic forcing scenarios show similar results, and the differences observed to each of them are due to the kind of AOGCM scenario used. A more in-depth analysis of the realistic scenarios results is made for selected drainage basins with a more or less comparable ice volume, but each with particular subglacial characteristics. So Pine Island and Thwaites glaciers are typical marine basins of the West Antarctic ice sheet, where most of the current ice mass loss is situated. Wilkes Land is a basin of the East Antarctic ice sheet with the potential for instability. And Enderby Land is part of the East Antarctic ice sheet, where the bed is mostly lying above sea level and where the contact with the ocean is limited. You can see on these histograms, so pay attention because the vertical scale is different for each basin. The highest mass loss occurs in the marine basin of Pine Island and Thwaites glaciers, followed by Wilkes Basin. For all the basin, the viscous sliding, so when m equal to 1, has the lowest sensitivity, but higher plasticity of the resliding law does not necessarily result in a higher sensitivity. So for example, in Pine Island and Thwaites Glacier, it exhibits the highest sensitivity for m equal 2, and for Wilkes Land, this is for m equal 5. You can also see that the teal model, so in orange in the histogram of Enderby Land, is less sensitive there because of the lack of saturated teal in this basin. So the complexity in response can be attributable to other factors such as increased accumulation rates and the relatively weak ocean forcing from the forcing scenario. In summary, in a basin level, subglacial hydrology has a more uncertain effect on the response of the ice sheet to forcing from global climate models. So to conclude, the basal sliding law is the dominant factor, but subglacial hydrology between ice and bed or inner till modulates the basal sliding response of the Antarctic ice sheet to climate forcing. Subglacial hydrological models that lead to low values of the effective pressure in the grounding zone, so HAB and SWD, increase ice sheet sensitivity to forcing, especially for extreme forces scenarios. And also this dependency is less clear in the realistic forcing scenarios. On a basin level, subglacial hydrology has a more uncertain effect on the response of the ice sheet to forcing from global climate models. So thanks for your attention. I hope I have succeeded in showing how important and how interesting subglacial processes were in Antarctica, and that you will not hesitate to read my paper to learn more.
Yeah, thank you for your interesting talk. And then we come to our last speaker for today, which is Danielle Halle. And she is a PhD candidate at the University of Waterloo in Canada. And she uses field methods to investigate the changing in ice fraction in the shallow firn layer on the Devon Ice Cap. She's also a national relations coordinator at the Association of Polar Early Career Scientists in Canada. And you're still in the...
Yes. Now it should be full screen.
Yeah, now you're in presenters mode.
Perfect. Okay, thank you for the introduction, and thank you for having me here today. I'm gonna give you guys a talk about the past 2 field seasons of my PhD. I'm now in the 3rd year in my PhD at the University of Waterloo in Canada. And my talk today is about the changing ice fraction in the shallow firn layer of Devon Ice Cap in the past 10 years. So I just want to start with some acknowledgements to say that all of our fieldwork takes place on Inuit Nunavut, which is the homelands of the Inuit in Canada, and to give acknowledgements to everyone on this project. So from the field team to people who are providing climate data, to my supervisors and Fern core data. This work would not be possible without everyone. So my project takes place on Devon Ice Cap, which is located in the dotted circle on the map. And this is one of the largest ice caps in the Canadian Arctic. On the right-hand side, there's a radar image from spring 2022. And here it's showing the different zones on Devon Ice Cap. But in most recent years, there is a melt that extends up to the summit. And my talk focuses on the Fern, and I'll just give a quick background of why it's important to understand what's happening on the Fern layer for Devon Ice Cap. So in years of extreme melt or intense melt events, the Fern layer allows for meltwater to percolate into the empty pore space and to refreeze and be retained as mass instead of running off and contributing to sea level rise. And in years of extreme melt or higher melt events, when refreezing occurs and thicker ice layers accumulate in the Fern layer, this can make it more difficult for future meltwater to be stored within the Fern layer. And this is a figure from Noel et al. In 2018, where they showed refreezing rates in the Canadian Arctic. So specifically in the Northern Canadian Arctic, refreezing still occurs at higher elevations within the Fern layer and is a really important mechanism for mass retention, and is the reason for why mass balance has remained near balance up to the 1990s is due to refreezing within the Fern layer. Whereas in the Southern Canadian Arctic, the Fern layer has been depleted or saturated and is no longer able to retain meltwater. And most of the meltwater that occurs manifests as runoff. So some motivation and background for my work. Also in 2012, a group of glaciologists drilled into Devon Ice Cap. And here they were trying to understand the changes in the shallow Fern layer from 2004 and 2006 and compared their Fern cores in 2012. And here what they found when they compared the Fern cores from the two time periods is that there had been an increase in the number and the thickness of these ice layers, and this has shifted to higher elevations on Devon Ice Cap. This is a photo from this paper where they were using infrared photography to document the Fern core stratigraphy. And a bit more background and motivation. So this work from Ashmore and others in 2020, they did modeling work on Devon Ice Cap. And here they were trying to understand how impermeable layers on the ice cap affect runoff and refreezing capacity. But I just want you to focus on the 2 years, 2012 and 2016 here. And what you can see is the yellow layers represent the higher density or ice lenses that had formed in 2012. And then 2016 was a cooler year on Devon Ice Cap. And it shows that that higher density ice layer was buried and that the Fern layer on top of this ice layer had been replenished. So my project is focusing on how the Fern layer has changed in relation to past work that has been done on Devon Ice Cap. And here I was using the exact same infrared camera as Bouzeau et al. Used in 2012. And this is an example of the infrared photography on the top right corner of the slide. And here you can clearly see the difference between icy Fern and the ice layers. And as well, we are documenting the stratigraphy of the Fern core and measuring the bulk density of each Fern section. And you can also see in the top right image is a tarp that is blocking the sun when we take the infrared photographs. So in addition to The firn cores, we're also using automatic weather station data. So here's a map of Devon Ice Cap, and along the mass balance transect, which goes from Sverdrup Glacier on the map to near the summit of the ice cap at DV1H. And each red square that you see on the map is where we have weather stations. And this pop-out photo is an example of how that looks, where the weather stations are collecting air temperature and snow depth. And then on the southwest transect, which you can see are stars that are hollow. This is where we extracted the firn cores, and this is also the exact same sites where the firn cores were extracted in 2012 from Bouzeau et al. And there's no weather stations located along this transect, so we're also using climate model data, which was downscaled and BICE adjusted from ERA 5, and also RACMO 2.3 from 2000 to 2019. So we'll go straight to the results now. So just to walk you through the slide, on the y-axis is the depth of each firn core, and it's always going to be the firn core from 2012 on the left-hand side, and then I'll show you our results from 2022 on the right-hand side. And the yellow colors are the ice within the firn layer, and these blue colors is firn. And the deep purple is no data. And to draw your attention to the right side of the slide, I'll be walking you through 3 different sites from the transect. And we'll start at the highest elevation site, which is at site 1, which is around 1,800 meters above sea level. And when we compare the firn cores from 2012 to our results from last spring in 2022, we can see that there was a decrease in the ice fraction in the top 75 centimeters. And this decrease was about 18% in the top 75 centimeters and 9% decrease in the top 200 centimeters. We see a similar pattern at the mid-elevation site, which is around 1,700 meters above sea level. And here there's a decrease in the ice fraction in the top 75 centimeters of 27%, and again, a decrease in the 200 centimeters depth of 32%. The last example I'll show from our results is at the lowest elevation site. And at this site is where we saw the largest decrease in ice fraction. So between 2012 and 2022, there was a decrease by 77% in the ice fraction in the top 75 centimeters. And when we compare the bulk density at all sites, we also see a decrease in bulk density at all sites, except for at the highest elevation site, which I'm still not sure why that is. But to look into why we have seen a decrease in the ice fraction at all sites from 2012 to 2022, I was using the climate model data to calculate positive degree days. So to walk you through this figure, on the, I don't know, for you guys, maybe it's the left-hand y-axis is the mean annual positive degree days. And then on the other y-axis is mean annual air temperature. And then between 2019 and 2020, there's a shift in climate models. So after 2019, it's the ERA 5 data. And if you look at the difference between the mean annual air temperatures, you can see this positive offset between RACMO 2.3 and ERA 5, which explains why we see this huge increase in positive degree days between those time periods. But across the entire time series, you can see in 2022 that this has the lowest positive degree days throughout the time series, which means that it was a fairly cool year in the Canadian Arctic in terms of firn conditions and climate. So this is also reflected in the glacier mass balance record. So this is the glacier mass balance record since 1959. And here you can see since since the start of the record that there's a relatively stable pattern of near balance on Devon Ice Cap, and then at the turn of the century, there's a more negative slope that occurs, and these were the conditions when the 2012 Fern cores were extracted. And then since then, there's this positive upward slope in glacier mass balance on Devon Ice Cap due to this large interannual variability that we're seeing now. So to draw those patterns to more of a pan-Arctic scale, there's a paper from Saskin and others from last year, and they were looking at the correlation of glacier mass balance with the northward heat flux. And the results that you see on the diagram here, the blue shows areas that are negatively correlated with the northward heat flux and glacier mass balance. So in the Canadian Arctic, it's showing this negative correlation, which means the northward heat flux is now moving further south in the Canadian Arctic and coming up along the eastern coast of Greenland, and could partially explain why we've seen this replenishment of the Fern layer in the past spring. So our results also confirm the hypothesis of modeling work from Ashmore and others in 2020, where they had predicted that in 1 or 2 cooler years, you can see this replenishment of the Fern layer, and that agrees nicely with our results from field data. To give you guys direction of where I'm headed next with this, I hope to have more of a spatial analysis of the entire Canadian Arctic and to understand if there was a replenishment of the Fern layer throughout the Canadian Arctic using radar data. And I'll do this using glacier zone classification maps in Google Earth Engine. But in the near future, I'll be collecting more field data also to be used in image interpretation and to understand if this replenishment of the Fern layer has continued into this following year. So takeaways from the talk is that there has been a decrease in the ice fraction between these 2 time points on Devon Ice Cap, which is potentially due to the coolest year on record since 2000 in the Canadian Arctic. And I want to understand if this replenishment of the Fern layer means an increase in meltwater storage capacity, and the next steps will be to investigate this at a Canadian-wide Arctic scale. So thank you very much for your time and happy for any questions.
Thank you for your nice talk. And yeah, with this, I'll also repeat the question. Are there any talks, any questions? Roland Barner has a question.
Hi, another great talks today as we're getting used to with IGS. I have a question for Danielle. I think you showed that in a few years prior to your very cold season, there was looked like a record high positive degree day year. And so I'm curious, I don't have a feeling for the accumulation on the Devon Ice Cap. How many years back in time are you seeing in these cores, and do you see previous horizons?
Yeah, that's what I'm not sure about, how far back in time we're seeing in the shallow Fern layer. I imagine at the higher accumulation areas, it could be around 4 to 5 years that it goes back in time. And then at lower elevations, a lot of it is getting melted and washed away. Yeah, so I think 4 or 5 years is what we're seeing in the top 2 meters at higher elevations.
Okay, so am I right in thinking that around 2020 you had a very high melt season?
Yeah.
And I'm just thinking in terms of the modeling you showed, these big lenses don't disappear. They just sort of subduct into the column, and I was just wondering whether you'd been able to track any of those.
Yeah, that's something that I would like to be able to do. I think just looking back at the results, you can see the ice layers are still present, but it's hard to match them up to the exact years.
Yeah.
So I think that's something I'd like to do later. Yeah.
Do you have sampling of things like water isotopes that would give you a seasonal or time profile down the core or not?
I do not have that, no.
Okay, thank you very much.
Thank you for your question.
Okay, are there any more questions? Roger has one.
Yeah, thanks very much. Thanks to all three speakers. But again, it's a question for Danielle. You said you're planning to do some radar there. What sort of depth, what sort of resolution are you aspiring to get with that? Some of those ice lenses are pretty darn thin, and some aren't, which is great. I just wonder what your targets are.
Ooh, I don't think I mentioned the radar. Or the radar that I did mention would be the satellite imagery, but I am actually planning to use GPR this spring. And we will be using a 500 megahertz unit. And looking, I think that should be able to penetrate 20 to 40 meters below. But I guess that will depend on the location and thickness of the ice layer, as you said.
Yeah, I realised you didn't say anything during the talk. It was just at the end where you said that's what you were planning to do. I just wonder what your aspirations were for geophysics being useful to your world.
Yes, yes.
Smashing,
yeah.
Thanks.
Thank you for your question.
Okay, and Andrei, you have one?
Well, thank you for nice talks. I have a question to Erik. You have very good seasonal fluctuations in calving front positions, different for different glaciers. Are they in some way related with seasonal ice surface velocity fluctuations or something like that?
Yes. So I think I know I talked about this one example of like this Harald Moltke Moray, which is like the surging glacier. And there we see like really obvious examples of that we have like this fast retreat after the surging phase. But I think even for like glaciers which are not surging glaciers, there's always an interaction between those different aspects like surface elevation change, velocity change, change in calving front. So it's a complex system. And I think with the calving fronts, we basically work on this one wheel or this one cog in the system to improve it, to basically improve the understanding of everything. So I think we always have to look at the whole system if we want to make assessments or analysis of certain glaciers.
Thank you.
Okay, are there any more questions? Otherwise, I would have a question to Elise. I think you briefly touched it in your talk, but you said that the different basins are differently sensitive to the sliding law. And can you maybe say a bit more about why is that, and can we characterize it, and what can we learn from that?
The thing is, the results I show about the basins is you do a global analysis, and after you analyze the results by basin. So the thing is, I think you have a lot of parameters were not taken in account that you could have a higher resolution. So for now, I'm studying the same parameterizations of the subglacial hydrology, but with higher resolution for each basin. Like that, you will avoid all the stuff you can see have more parameters not taken into account in the basin analysis. So that's the first, because also you have a parameterization at the grounding line for the ice flux taken in account for global analysis, but not at higher resolution. So I would like also to avoid this and try to evaluate if this parameterization has a lot of effect in comparison to basal sliding loads. So that's the first point. But yeah, the thing is, each basin has their own sensitivity, and as I explained, if you increase the plasticity, you won't especially increase the sensitivity depending on the basin.
Okay, thank you. Then, yeah, looking forward to see what comes out of the more detailed models. Yeah, are there any more questions? Okay, Roger has another one.
Yeah, thanks. Also for Elise, how thin does the water layer have to be before it matters to you? You were talking about having thin water films at the bottom of the ice.
Yeah,
Is it just millimeters, fractions of millimeters, centimeters, that sort of thing?
It depending on the ice thickness, obviously. So the thing is, here we consider a global model of few millimeters, and we limited the water thickness to have something consistent. You cannot have meters of subglacial water thickness everywhere and still have your ice sheet. So yeah, I think it's really depends on the ice thickness. That's the really water thickness which will have a big influence.
Sure. Yeah, I mean, I'm just thinking it from a geophysical imaging point of view, because I'm always extremely nervous about radar or seismic models that just represent the base of the ice as an individual isolated layer, and thinking about what thin layers, compound reflections and so on we may be missing and so on. So yeah, nice to hear your perspective on it. Thanks very much.
Okay, are there any final questions? Okay, it doesn't look like it. Yeah, then I want to thank again all three speakers for three really nice talks. And do we have an advertising slide for the talks next week? Maybe we can bring this up now.
I'm struggling to put it onto a full screen, to be honest. We have a talk next week on GLAMBI, an intercomparison exercise of regional and global mass balance changes. And the speakers are Livia Jacob and Michael Zemp. So that's the talk for next week.
Okay, so yeah, then hopefully see you next week again. And yeah, again, thank you everybody for listening and for especially for presenting to the three early career scientists today. And then yeah, hope to see you soon again.
Maybe remember to send it to me when you've got things sorted.
Goodbye.
It's in some strange format, Magnus, that I haven't quite worked out. I'll get it to you as soon as I can.
Okay, sounds good.
Speak soon.
Yeah, cheers.